Today we shall discuss some applications of the Langevin equation that we have described in the previous class. So I would like to start with the equation itself and give some previous applications. So if we consider the Langevin equation written for the position x, then the second derivative with time plus gamma x dot equals 2 epsilon gamma. So we will write it now this way, where W is the Brownian noise. And so a popular problem was the following. So this is problem 1. So suppose you have an interval from 0 to L, and the particle is entering at 0. So we have x0 equal 0. And now we need to specify the velocity. So the velocity, which is x dot of 0, it's a number v0 which is positive, so that the particle enter. So let me remind you that the Langevin equation in this form can be also written in a two-dimensional system by writing x dot equal velocity, and the velocity v dot, which is exactly the acceleration, is minus gamma v plus 2 epsilon gamma w dot. So then if we enter a particle here with a velocity, so this is here position x, and I draw in the perpendicular axis the velocity. So we have v0 here. And so the question is then, is an entering particle going to reach here the right part at L, or is it going to escape first on the left? So in other words, we can define the time tau L, which is a time left, which is the first time. So we'll write it this way. This is the infimum of the time t, such that the particle exit on the left. That is, this is the first time that x of t equals 0. Condition that initially it was at 0, and so x of t equals 0, and the velocity on this, it leaves the domain, let's say, with a negative velocity, because it cannot escape with a positive velocity, obviously. And the initial position was x0 equals 0. Now we can do the same, we can define the time on the right, which is the first time that the particle escape from the right, so which means x of t equals r, when initially x0 was equal to 0. So this problem is quite interesting because this is not, and again here, so when it escape, we have to say that the velocity on the right is positive. So, for example, what's the probability? So a question of interest is, what's the probability that the particle escape first? What's the probability that the particle escape first on the left before right? Which can be written this way. And then the question is, of course, how to evaluate such a quantity. So this, I will leave this more or less open because this is not a trivial question. Let me just remind you that for this we should use the Fokker-Planck description. So the Fokker-Planck description, so I refer to the class about Fokker-Planck, which basically allowed us to derive the equation for the probability distribution function, which is dp/dt. So dp/dt and this is equal to the operator L of P. And L of P, let me characterize it in the next slide. So by definition, L of P, so I refer to the class for the definition of how to derive the Fokker-Planck equation. This is minus, so we have the first order term, minus V, and this is dp dx, plus, so beta epsilon, and now we have the second order term, ddp dv squared, and then we need the second term in V, which is the first order derivative in V, ddv beta v, plus, so if we have, so I will write it this way, if we have a field, a vector field, we can add here the field dv dx, and then this is multiplied by p. This is when the equation reads x dot plus gamma x dot plus a potential phi prime of x equals 2 epsilon gamma w dot. And what is interesting with this form is that the operator can always be written divergence of the field of the flux, where J here has two components. One is Vp and the other is minus beta V plus d phi dx multiplied by P minus epsilon gamma multiplied by dp dx. So for example, this allows us to define, for example, the flux. So the flux inside the domain, this domain, 0L, so the flux in here is simply J dot normal of the domain, which is only in the x direction, and then we have to integrate. For example, if we look the flux in, it means particles are pointing towards the domain, so V has to be positive, so this is integration from 0 to infinity. So now this is simply V multiplied by P, X, and V. So if we look at the steady state solution, this is dV, and we have to integrate 0 to infinity. So this is by definition the flux inside from the left. So this is from the left. So I will now just give some references about, for example, how to analyze this partial differential equation by using expansion in beta. So this I will refer simply to the following reference: Eisenberg, and there's another author, and Schuss, and this is Journal of Chemical Physics, and the year is 19 95. This is volume 102, and this is the number 4. And there is also another reference, a much older reference, from the mathematicians who developed what is called the albedo problem. And so the reference is Siam Journal of Applied Mathematics, so Siam of Applied Mathematics. And there are two papers, one in 1986 and the other one is 1989. And one of the authors is David Livermore. With a capital L. Okay, and so this had an application in the following question of the channel in biophysics. So if we have a channel which is a little pore in the membrane, so this is the extracellular space, and this is intracellular space. And so ions, which can be negative or positive, can actually go through here and are selected. And so usually there is here complicated potential, and there's an ensemble of molecules that create a potential well. And so the question in the field was compute the flux when the channel open. What is the flux of ions? Another difficult question, which is partially solved, is how ions are selected, which we're not discussing here. So we can use the previous formalism to compute the flux. So here the interesting quantity would be what is the probability of an ion entering in the left that will exit in the left. So this can be written as the flux. So let's call the flux that a particle started on the left, arrive on the left, normalized by the flux that when the particle started on the left, it ends on the left, plus the flux when the particle starts on the left, it ends on the right. And the flux can be calculated using the J that I've written in the previous slides. So again, if you are interested in a specific calculation, you just go to see the reference Journal of Chemical Physics 1995 of Heisenberg. So, and this was important not to use the Smoluchowski limit of the Langevin equation, because an ion that arrive here at the boundary, if it doesn't have any velocity, then the ions cannot go through. It's not well defined what is the beginning of a channel, what is the end of the channel, and also for simulations. Without Langevin, there is no notion of velocity that can be manipulated, or no notion of velocity at all. So the Langevin equation is the closer description for the motion of particle in an ion. And for example, here the potential can be, so for example, if we think about a two-state potential where we now want to describe two ions, we can say that, so another model, description model of a channel with two ions, So then in that case, we can write two Langevin equations for the first one and the second one, plus gamma x dot 2 plus, so we can use an energy of interaction between 1 and 2. So this is x1, x2. Plus, there can be also direct interaction, which we call phi prime of x2, that will only depend on the position of x2. So now this is equal to noise. So this is 2 epsilon gamma square root and W2 dot. And now we can write the same for the first equation, for the first particle, which is x double dot plus gamma x1 dot plus an energy of interaction V prime, and so here we have a V prime of x1 and 2, x1 and x2, plus a term which is phi prime of x1 equals noise, which is 2 epsilon gamma square root W1, which is a noise for the first particle. And this energy of interaction can be a Lennard-Jones term, which is simply given by V of x1, x2 equals, this is the Lennard-Jones term, which is C1 divided by x1 minus x2 to the power 12 minus a constant C2, which is so a constant C2 x1 minus x2 to the power 6. So this can be used to, so for example, we can add in the model that in addition, instead of this Lennard-Jones force, we can say, for example, x1 minus x2, x1 minus x2 is larger than a certain distance a, so that it prevents x1 to collide to x2, and so this is equivalent in a domain x1, x2 in this region to have an exclusion bound, that is x1, x2, and we get here some kind of a band of exclusion here of size 2a. Okay, so now I would like to so using this framework, it's possible to make applications, for example, to make simulation of two particles in a channel and to evaluate some properties, although it's also interesting to have a complete calculation, complete analysis. So the next example comes from amplification. So how do we amplify? Amplification with a single particle. So suppose we have a particle that at time 0 becomes activated during a random time tau, and during this random time the particle can have a Brownian motion, and suppose the size of the particle is epsilon, so this is its size, and it makes a Brownian motion in an environment where there are a certain density rho of particle. So this is a density of particle that can be excited, of particles that can be activated. So this particle can be activated when the particle, let's call P star, hit them. So then the quantity we will be interested in is the surface that this particle P star will explore. So one possibility is to look at the ball of radius epsilon centered at x of s, take all the balls for s between 0 and the time it is activated, tau, and look at the surface. So this is exactly the Wiener sausage. And of course we'll be interested here in the expectation of this quantity. So we have to average this over all realization. So if we are averaging over all realization, it will be interesting to get this quantity as a function of tau and epsilon. So this is actually well known. And for example, in dimension 2 and 3, this has been calculated. So if tau is now, so this is pi tau, tau is the average time divided by, in dimension 2, log of 1 over epsilon. And this is when tau is small. So this is for epsilon small and tau small. And in dimension 3, it is of the order of 1 divided by epsilon constant tau. And so with this, we can now get an estimate of the number of molecules that can be activated. So the expectation of the number of activated molecule is, it's an overestimation because obviously a particle that has been activated once through the random walk, because the random walk is recurrent, then it will pass through the same point many times. So actually what would be really necessary to do this calculation properly is to use the self-avoiding random walk. So an overestimation is given by, in dimension 2, pi tau log of 1 over epsilon multiplied by the density. And if then there is a certain efficacy of this activation, we can multiply by this probability. This is the probability to be activated. Okay, so now we have seen from this example how Brownian motion and the Langevin equation can be used in some physical and biophysical property. So as an exercise, I invite you to look at the same question with self-avoiding. So question, find this estimate, find an estimate for a self-avoiding random walk. And I will stop this for applications, and we will then see in the next lectures some other application of Brownian motion.